This class we are going to discuss about properties of inverse trigonometric functions. The first property is sin inverse of sin theta is equals to theta under the condition theta belongs to closed interval minus pi by 2 comma pi by 2. Cos inverse of cos theta is equals to theta when theta belongs to closed interval 0 comma pi. That is the reason I told you have to remember all these principal branches. Tan inverse of tan theta is equals to theta if theta belongs to open interval minus pi by 2 comma pi by 2. Secant inverse of secant theta we can write theta only when theta belongs to closed interval 0 comma pi excluding 90. Cosecant inverse of cosecant theta we can write theta if theta belongs to closed interval minus pi by 2 comma pi by 2 excluding 0. Cot inverse of cot theta we can write theta if theta belongs to open interval 0 comma pi. See here one particular idea I want to prove here. Sin inverse of sin theta we are writing it as theta. So for that what I am doing here is I am assuming sin theta is equals to x. You can observe theta belongs to minus pi by 2 comma pi by 2. That's why whenever theta belongs to closed interval minus pi by 2 comma pi by 2, definitely the value of x is also belongs to closed interval minus 1 comma 1 or not. So now I can write theta is equal to from here sin inverse x, because theta is there in the principal branch, x is also there in the principal domain. So that's why theta is equal to sin inverse x we can write. Now I can write this one as sin inverse of what is x? X is nothing but sin theta. So that is the reason we are getting sin inverse of sin theta is equals to theta. Similarly we can prove the other results. Similarly this is the second property, sin of sin inverse x is equals to x when x belongs to closed interval minus 1 comma 1. Cos inverse of cos x is equals to x if x belongs to closed interval minus 1 comma 1. Tan of tan inverse x is equals to x if x belongs to real numbers. Cot of cot inverse x is equal to x if x belongs to real numbers. Secant of secant inverse x we can write x when x belongs to all real numbers excluding open interval minus 1 comma 1. Cosecant of cosecant inverse x we can write x in the same x values. That's what we can write x belongs to minus infinity to minus 1 closed bracket union 1 to infinity. This meaning is the same as from all real numbers we are excluding open interval minus 1 comma 1. So this is having the same meaning here. Now I want to prove one particular idea. Observe here sin of sin inverse x is equals to x I want to prove. Now here no doubt we got the information x values belongs to minus 1 comma 1. Whenever x values are belongs to minus 1 comma 1, definitely theta is also lies between minus pi by 2 and plus pi by 2. Now here I am considering sin inverse x is equals to theta. So that means I am considering sin inverse x is equals to theta. From this we can write x is equals to sin theta, right? Now this is equals to sin of, in place of theta what we can write? Yes, sin inverse x we can write. So I can say x is equal to sin of sin inverse x. Otherwise we can also do it in this way, f circle f inverse of x, because we know g circle f of x we can write it as g of f of x. G circle f of x we can write it as g of f of x. That's why f circle f inverse of x we can write f of f inverse of x. Now this is f and this is f inverse, so we can write this one as x. The same meaning here, f of f inverse of x we can write directly You can see here the third property, sin inverse of minus x is equal to minus sin inverse x, tan inverse of minus x is equal to minus tan inverse x, cosecant inverse of minus x is equal to minus cosecant inverse x, whereas cos inverse of minus x is equal to pi minus cos inverse x, cot inverse of minus x is equal to pi minus cot inverse x, secant inverse of minus x is equal to pi minus secant inverse x. Just I want to prove this particular property. Sin inverse of minus x is equal to minus sin inverse x. So we got the information x belongs to closed interval minus 1 comma 1. Now here I am assuming sin inverse of minus x is equals to theta, because whenever x values belongs to minus 1 comma 1, no doubt minus x values also belongs to the same interval. So that is the reason sin inverse of minus x, that means theta values is also belongs to closed interval minus pi by 2 comma pi by 2. So x belongs to closed interval minus 1 comma 1, theta belongs to closed interval minus pi by 2 comma pi by 2. So we can write minus x is equal to sin theta. So from this I can write x is equals to minus sin theta. Now I can write further this one as minus sin theta. We can write it as sin of minus theta, right? Array x is equal to, we got sin of minus theta. Theta belongs to closed interval minus pi by 2 comma pi by 2, means minus theta is also belongs to the same interval. That's why you can find out minus theta is equal to sin inverse of x. Therefore I can write theta is equal to sin inverse x with minus sin. What is theta? Theta is nothing but sin inverse of minus x is equal to minus sin inverse x. The same way we are going to prove the next result also. Here I am assuming cos inverse of minus x is equals to theta. No doubt here x belongs to closed interval minus 1 comma 1. That's why theta belongs to closed interval 0 comma pi. Here we are taking cos inverse of minus x is equal to theta. That's why we can write minus x is equal to cos theta. Therefore we can write x is equal to minus cos theta. But this you can't write it as a cos of minus theta. But we know because cos of minus theta is cos theta only. So I am writing this one as cos 180 minus theta. Right? So cos 180 minus theta is equal to x we got. From this we can write pi minus theta is equal to cos inverse x. You can write only when pi minus theta is there in the principal branch. Pi minus theta is there in the principal branch, then only we can write this step. Because you see here x is equal to sin of minus theta. I written minus theta is equal to sin inverse x. The reason is minus theta is also present in the same branch, right? Now you can observe here, 0 less than or equals to theta less than or equals to pi. Multiply with minus, inequality changes. Minus pi less than or equal to minus theta less than or equal to 0. Now add pi, here 0 less than or equals to pi minus theta is less than or equals to pi. You can observe here minus theta is also there in the principal branch only. That's why we can write this step. Okay, so that's why we are getting theta is equals to pi minus of cos inverse x. But what is theta? Theta is nothing but cos inverse of minus x. So cos inverse of minus x is equal to pi minus cos inverse x. Similarly, we can prove the other. See here another property here. Sin inverse x plus cos inverse x is equals to pi by 2. Tan inverse x plus cot inverse x is also equal to pi by 2. Secant inverse x plus cosecant inverse x is equals to pi by 2. In this case, x belongs to minus infinity to minus 1 closed interval union closed interval 1 to infinity. Just here also I am going to prove this particular property. Sin inverse x plus cos inverse x is equals to pi by 2. Now I am assuming sin inverse x is equals to theta, right? The reason is x belongs to closed interval minus 1 comma 1 and theta belongs to closed interval minus pi by 2 comma pi by 2. So that's why we can write here x is equals to sin theta. But now sin theta we can also write it as cos 90 minus theta. Sin theta we can also write it as cos 90 minus theta. Now the step here, from this if we can write pi by 2 minus theta is equal to cos inverse x, you can write only when this pi by 2 minus theta must present in the principal branch of cos, because here we are applying inverse function. Inverse function definition we are applying means cos principal branch has to exist. That's why this pi by 2 minus theta must present in the principal branch of cos. That's why just we will check it here, because what the information given here, theta belongs to, that means minus pi by 2 less than or equals to theta less than or equals to pi by 2. Add, multiply with minus. If you are multiplying with minus, then it becomes minus pi by 2 less than or equal to minus theta less than or equals to pi by 2. Not affected much. You can see multiplying with minus. Here becomes a plus greater than or equal to. Here becomes minus greater than or equal. That's why same you will get. Now add pi by 2. Here pi by 2 addition 0 less than or equals to pi by 2 minus theta is less than or equal to pi. That means pi by 2 minus theta is there in the principal branch or not. So we can write this particular step. Now I can write cos inverse x is equals to pi by 2 minus, what is theta? Theta is nothing but sin inverse x. That's why we can write sin inverse x plus cos inverse x is equal. So this is another important property. Sin inverse of 1 by x is equal to cosecant inverse x. Cos inverse of 1 by x is equal to secant inverse x. But tan inverse of 1 by x is equals to cot inverse x when x is greater than 0. Tan inverse 1 by x is equals to cot inverse x when x greater than 0. Up to this part they mentioned in the NCI textbook. This one also required for objective exams. We can write this one as minus pi plus cot inverse x when x is less than 0. So tan inverse x is cot inverse x when x greater than 0 minus pi plus cot inverse x when x value is less than 0. So first of all I will try to prove this one. Just here I am assuming cosecant inverse x is equals to theta, right? Because x belongs to minus infinity to minus 1, x belongs to minus infinity to minus 1 union 1 to infinity. That means theta belongs to closed interval minus pi by 2 comma pi by 2 except 0, because at 0 it is tending to infinity. That's why excluding 0. Now from this I can write x is equals to cosecant theta, right? That means I can write 1 by x is equals to now sin theta, right? You can check theta is there in the principal branch only. At the same time 1 by x values also lies between minus 1 and plus 1. That's why we can apply here theta is equals to sin inverse 1 by x we can write. After this step we can write this one. The reason is theta is there in the principal branch of sin. 1 by x values also lies between minus 1 and plus 1. That's why theta is equal to sin inverse 1 by x. What is theta? Theta is nothing but cosecant inverse x. Cosecant inverse x is equals to we can write sine inverse of 1 by x. But what about this proof? Just I will try to discuss the proof of this particular one also. The first case is x greater than 0. That is the first case. Here I am assuming cot inverse x is equals to say theta. Cot inverse x is equals to theta. Then we'll get x is equals to cot theta or not. X is equals to cot theta, right? Now x is equal to cot theta and we got the information x greater than 0. Or x greater than 0 means cot theta is greater than 0. Where cot theta is positive, cot inverse x is equal to theta, and we are writing x is equal to cot theta means what? X belongs to all real numbers and theta belongs to open interval 0, pi. But we are proceeding the case with x greater than 0. So we got cot theta greater than 0. Cot theta greater than 0 in this interval where? In this interval theta belongs to first quadrant. That means theta belongs to 0 to pi by 2. Okay. So x is equals to, we got cot theta. Now I can write 1 by x is equals to tan theta. Check once. Theta is there in the principal branch. What is the principal branch for tan? Tan principal branch is open interval minus pi by 2, pi by 2. Now you can check here theta. Theta is there in this interval. In this interval means 0 to pi by 2. This is a subset of open interval minus pi by 2, pi by 2. That's why theta is there in the principal branch. So we can write this one as theta is equals to tan inverse of 1 by x. What is theta? Theta is nothing but cot inverse x. So we can write cot inverse x is equals to tan inverse of 1 by x when x greater than 0. Next, second case here I am doing when x is less than 0. X is less than 0 means what? Cot theta less than 0. Cot theta negative where? In this interval. In this interval cot theta is negative when theta belongs to pi by 2, pi. Theta present in this interval. Now the same information we got x is equals to cot theta. From this I can write 1 by x is equals to tan theta. But we can't write here. Here we can't write theta is equals to tan inverse 1 by x. Why we can't write? The reason is theta is not in the principal branch. Theta is not there in the principal branch. That's why we can't write in this way. Okay. So we will try to check. So we got the information pi by 2 less than theta less than pi. So we got this we can't write. That's why we are removing this particular portion. 1 by x is equals to tan theta we got. So pi by 2 less than theta less than pi. Now what I am doing is this I can also write it as tan of theta minus pi. Tan theta I can also write tan theta minus pi. Yes, tan theta we can also write it as a tan theta minus pi. We will check whether theta minus pi is there in the principal branch or not. We will check. Now you can check here pi by 2 less than theta less than pi. Subtract pi, then we will get minus pi by 2 less than theta minus pi is less than 0. Okay. So minus theta minus pi lies in the principal branch of tan. What is the principal branch of tan? Actually tan principal branch is minus pi by 2 to pi by 2. Here we got from minus pi by 2 to 0, which is a subset of this set. That's why we can write here theta minus pi is equals to tan inverse of 1 by x. So that is the reason tan inverse 1 by x we can write minus pi plus cot inverse x minus pi plus cot inverse x. We saw theta is cot inverse x only, right? So when x greater than 0 we can write So that's why tan inverse 1 by x we can write cot inverse x when x greater than 0, that is equals to, we can write. So observe here, tan inverse x plus tan inverse y is equals to tan inverse of x plus y by 1 minus xy when xy less than 1. Only this case is given in a class 12 syllabus. Okay, for board exam only this part is enough, but for objective ideas you require to know about these two also. Tan inverse x plus tan inverse y, we can write tan inverse of x plus y by 1 minus xy if xy less than 1. First of all, I will try to prove this case, because xy less than 1 means what? This is one case possible, both are positive, then product is less than 1 possible. You see here 1 by 2, here 1 by 2, their multiplication you will get less than 1. One is positive, the other one is negative, then also xy less than 1. Both negative, then also xy less than 1 possible. One is less than 0, the other one greater than 0, then also xy less than 1 possible. That's why xy less than 1 possible in all these cases. So in all these cases we can prove this particular result. Just observe here, I am assuming tan inverse x is equals to a and tan inverse y is equals to b. That is the assumption I am doing. Now from this we can write x is equals to tan a and y is equals to tan b. X is equals to tan a and y is equals to tan b. Now can you tell me here, a comma b belongs to open interval minus pi by 2 comma pi by 2, because as you know tan inverse x range is open interval minus pi by 2 comma pi by 2. That is the reason a comma b belongs to this interval, and or x comma y are any real numbers, but here xy less than 1 case we are proving. So now you can see the first case, any one of the case, any one we can do it. Suppose for the purpose of this I am trying to discuss this one. What is that? X less than 0. X less than 0 means tan a less than 0. Y greater than 0. Y greater than 0 means what the information we have? Tan b greater than 0. Array tan a less than 0. But we have the information a comma b belongs to this interval. In this interval where tan a is negative, yes, tan a negative means definitely a belongs to minus pi by 2 comma 0. But here tan b greater than 0, but we have the information b belongs to this interval. But in this interval where tan is positive, when b belongs to open interval 0 comma pi by 2, in this interval tan b is positive. Now a belongs to minus pi by 2 comma 0, b belongs to 0 comma pi by 2, but we know tan of a plus b. What is the formula for tan of a plus b? Tan of a plus b is equals to tan a plus tan b divided by 1 minus tan a into tan b. That is the formula for tan of a plus b. So we are getting x plus y divided by 1 minus xy. Array tan of a plus b is equal to x plus y by 1 minus xy. From this we can write a plus b is equals to we are applying inverse function definition. A plus b is equal to tan inverse of x plus y divided by 1 minus xy. You can write only when this a plus b lies in the interval minus pi by 2 comma pi by 2, right? If a plus b belongs to that interval, then only we can write. Now you can check here, a belongs to minus pi by 2 comma 0, b belongs to 0 comma pi by 2. Definitely a plus b belongs to these two sum belongs to minus pi by 2 comma pi by 2 only. Yes, a plus b is there in the principal branch, so this step is valid. What is a? A is nothing but tan inverse x. What is b? B is nothing but tan inverse y. So that's why tan inverse x plus tan inverse y, we got tan inverse of x plus y by 1 minus xy, right? So that is in this. Check the next, which I am going to prove this particular idea. What is saying in that particular idea? X greater than 0, y greater than 0, and x into y is also greater than 1. Or x greater than 0, y greater than 0, x into y is more than 1. From this I can write this tan of a plus b must be, that means this total value must be, tell me, x positive, y also positive, x into y is more than 1 means this total value is less than 0. That is the information. At the same time we are taking x greater than 0, but x is nothing but tan a greater than 0, right? And y also greater than 0, that's why tan b is also greater than 0. Now I can write a belongs to 0 comma pi by 2. Similarly b also belongs to 0 comma pi by 2. Now you can observe here we are getting a plus b belongs to 0 comma pi. Those two addition we are getting a plus b belongs to 0 comma pi. But what the information we have here, we got the information tan of a plus b is equal to x plus y by 1 minus xy, which is a negative, which is less than 0. But in this interval where tan is negative, yes, when a plus b belongs to pi by 2 comma pi, definitely a plus b present in this interval. In this interval only tan you will get negative. So from this we can't write a plus b is equals to tan inverse, you can't write. Why? The reason is a plus b is not there in the principal branch. It is not there in the principal branch, so we can't write. That's why what to do now? That's why what I am doing, observe here, tan of a plus b, we can also write it as tan a plus b minus pi, also we can write this tan a plus b, we can write it as tan of a plus b minus pi is equal to x plus y divided by 1 minus xy. Okay sir, you are writing tan of a plus b as tan of a plus b minus pi, but what is the guarantee? This is there in the principal branch. Observe here, the information what we got is pi by 2 less than a plus b is less than pi. That is the information we have. Now subtract pi, here subtract pi, you will get minus pi by 2 less than a plus b minus pi is less than 0. Now you can check a plus b minus pi is there in the principal branch, because the tan principal branch is minus pi by 2 to pi by 2 open interval. Now a plus b minus pi is there in the principal branch minus pi by 2 to 0. That's why we can write this one as a plus b minus pi is equals to tan inverse of x plus y divided by 1 minus xy. Therefore we are getting a plus b is equals to pi plus tan inverse of x plus y divided by 1 minus xy, right? So what is a? Tan inverse x. So that is the way we can prove the other result also. X less than 0, y less than 0, xy greater than 1, then tan inverse x plus tan inverse y, we can write minus pi plus tan inverse of x plus y by 1 minus xy. Only the first one required for the board exam. See, the same way we can prove this particular results also. Tan inverse x minus tan inverse y is equals to tan inverse of x minus y by 1 plus xy when x into y is greater than minus 1. That we can write it as pi plus tan inverse of x minus y divided by 1 plus xy. We can write when x greater than 0, y less than 0 and x into y is less than minus 1. And in other case, this is the possibility, minus 5 plus tan inverse of x minus y divided by 1 plus xy. All these proof we can do just like as the earlier one, but proofs are not required, but we have to remember these particular ideas. Let us see, there is another one also here, tan inverse x plus tan inverse y in general. Tan inverse x plus tan inverse y plus tan inverse z, we can write it as tan inverse of x plus y plus z minus xyz divided by 1 minus xy plus yz plus zx. That is tan inverse x plus tan inverse y plus tan inverse z. Suppose he is asking tan inverse of x1 plus tan inverse of x2 plus tan inverse of x3 plus and so on plus tan inverse of xn. But then what to do? That we can write it as tan inverse of s1. What is the meaning of s1? Sum x plus y plus z, like that x1 plus x2 plus x3 plus and so on plus xn minus, next one is what? S3, sum of the product of the terms taken 3 at a time, plus S5 minus S7, all odd you will get in the numerator, alternatively plus minus and so on, divided by what we will get in the denominator, 1 minus, here we got S2, right? What is S2? Sum of the product of the terms taken 2 at a time, 1 minus S2, next we will get S4, next we will get S6 plus and so on. This is the way to write the generalization, just how we discuss. This is S1 and this